This video is a review of electron configurations, a 1,000,000% review from first year chem. Electron structure has not changed in the last year or so. Now what I would suggest is getting out your periodic table packet, because we're going to mark in the orbitals and the energy levels, and so as you watch this video you may need to pause it and bring it back so that you can make these markings on your periodic table as well. So we've been looking at these orbital diagrams, little boxes and arrows that help us to visualize where all the electrons are found in an atom. And they're great, but eventually who wants to draw out a whole bunch of boxes and arrows when the atoms start getting a little bigger? And who wants to memorize the order that the orbitals fill? Do I need 1 box, 2 boxes, 3 boxes, 5 boxes? And so the periodic table can predict all of that. It's a pretty fascinating tool. And in order to use the periodic table to predict electron configurations, we're going to make some markings. So first thing we're going to do is draw a box around the first 2 columns. And then somewhere in that box we're going to put an S. And we call this the S block. Every energy level has an S orbital. So down the side, if it's not marked in on your periodic table, we're going to number. Row 1 is going to be energy level 1. Row 2, energy level 2. Row 3, energy level 3. Row 4, 5, 6, and 7. The rows going across represent the energy levels. So far we've got 118 elements known today, and the electrons only fill 7 energy levels. Now this periodic table is kind of missing some of those elements down in the bottom corner, like 116, 17, 118, but I would predict that the next element, 119, would maybe have to start an 8th row at the bottom of the periodic table. If the pattern falls true, I think that the next element, 119, will start an 8s orbital when we find it, right? So we put a block around the first 2 columns. We call it the S block. We number down the side 1 through 7. There's an S orbital in every energy level 1 through 7. Now S orbitals can hold 2 electrons. That's why this block goes across 2 elements, to represent the fact that 2 electrons fill the S orbitals. Now there's one element that we've got a little identity crisis with, and that's helium. So this would be helium kind of in this upper corner. For electron purposes, helium kind of belongs next to hydrogen. This would be hydrogen. This could be helium. Now, helium is not a metal like beryllium, magnesium, and calcium. He's a non-reactive gas. So we leave him on the far side with neon, argon, krypton, xenon, radon. But for electron purposes, we do kind of put helium in the 1s row. Helium does fill the 1s orbital with 1 and 2 electrons. And now watch what happens. Let's say I'm doing an electron configuration. You always start with element 1, hydrogen. The first orbital filled is always the lowest orbital, the 1s, and it's filled with 2 electrons. So you go 1s, and the number of electrons is that little superscript. First energy level, S-shaped orbital, like a low energy orbital, that can hold 2 electrons. And if you follow across now, there would be no other elements in the first row of the periodic table. So then electrons 3 and 4 would go in the next available orbital. So electrons 3 and 4 belong to lithium and beryllium. This would be lithium and beryllium. Now I'm in the second energy level. The S block, it can go across up to 2. If I were to go to S1, I would be at lithium. If I say to S2, I'm at beryllium. Now the second energy level does have p orbitals. And so on your periodic table, we're going to put a big box around this section of the periodic table. So this is going to be like boron all the way across to neon. Boron across to neon. This is your p block. The p block goes across 1, 2, 3, 4, 5, 6 elements because a total of 6 electrons can fit in the p orbitals. There are 3 p orbitals that each hold 2 electrons. Total of 6. Now the other thing that I would do when I get over to the p block, I'm going to remind myself that this is the 2p. Even though it's the top row of the p block, there is no such thing as 1p. This is the second row or the second energy level. So 2p. And then I continue numbering all the way down. 3, 4, 5, 6, 7. All right, I kind of remember this now. So if you are electron 5, you're in the 2p. Somebody like boron would be 2p1. Carbon is the next element in. Carbon would end 2p2. Nitrogen would be 2p3. Oxygen is 2p4. Fluorine is 2p5. And then somebody like neon would end 2p6. And now that's it for the second energy level. So then you go to the third energy level. The next available orbital would be in the third energy level. This is electrons 11 or 12, s orbital. If I'm sodium, it'll end 3s1. If I'm beryllium, 3s2. And so on. We keep going. Electrons 13 through 18 would now be in the 3p. So in the 3p, 13 through 18. If I'm argon, I'm 3p6. I remember this. But now here's where things get a little funky. We do know that in the third energy level, there are d orbitals. But if I follow the order of the periodic table, after argon, 18, elements 19 and 20 look to be in the 4s for maybe 2. So this over here would be potassium, and this would be calcium. And you say, but wait a second, I feel like we should go 3s, 3p, 3d. And we kind of saw this issue a little bit with orbital diagrams. The order that the orbitals fill is always low energy to high. Overall low energy to high energy. And so we got a little issue here. In this midsection of the periodic table, this is called the D block. We'll put in a D there. The D block goes across 10 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9. You've got to be kidding, 10. It goes across 10 elements to represent the fact that there are 5 d orbitals that each hold 2 electrons for a total of 10. Now, again, somebody told me that the Ds don't start till the third energy level. So the first row of the D block is the 3D by scandium number 21. And then I go 4D, 5D, 6D. So according to the periodic table, after calcium 4s2, it sure looks like the next orbital would be the 3D. And it could go across up to 10. If I were 3D10, I'd be at zinc right now. And again, people will look at that and say, ooh, I don't think that looks right. I feel like we should flip-flop the 4s and the 3D. But we said it's right. That you got a couple things going on here. Number one, 4s. So 4 means we're in the 4th energy level. So the electrons are in a pretty big orbital. the electrons can start like trickling a little bit farther away from the nucleus. It's a big orbital. But an s orbital is a low energy orbital, and there's only one per energy level. So its only claim to fame is that it's big. It's one big orbital. But then you've got the 3Ds. All right, so 3D means third energy level. So they're a little bit smaller. Like on average, the electrons are maybe a little bit closer to the nucleus. But D orbitals are really high energy orbitals. And there's 5 of them. So now I've got like 2 stars. I've got high energy orbitals, and there's a lot of them. There's 5 of them. The only miss here is that they're a little bit smaller. The electrons are a little closer to the nucleus. I think we use the analogy of like a boxing match, where you've got one big, beefy boxer. And he's so big that he's kind of slow and low energy, like a 4s orbital. There's only one boxer. He's slow, but he's big. Versus in the other corner of the ring, the 3D orbitals. There are 5 of them. And these guys are super jacked up on Mountain Dew and Pixie Sticks, and they're really high energy. There's 5 of them. But they're a little bit smaller. They're a little smaller dudes. But again, like it's a boxing match, 1 versus 5. The one guy is big. The 5 guys are a little bit smaller. But the 5 guys are super high energy, and the one guy is kind of low energy, slow. And we say, who wins? The 3D orbitals. The 5 little high energy guys win the boxing match. When you take all factors into consideration, the 4s orbital really does have overall less energy than the 3Ds. So the periodic table will tell you the right filling order. And if you mark it in like this, you'll remember, if I'm zinc, which would be 3D10 over here, after I hit the 3D, now I'm going to the 4p, and I could go across up to 6, and I'd be at krypton. And that same pattern is going to happen throughout the rest of the periodic table. Next, I would hit the 5s for 2. I'd be at the 4d for up to 10. And then I'd be at the 5p for 6. So it takes you about 30 seconds to mark up your periodic table. S block, P block, D block. S's start in the first energy level. P's start in the second. D's start in the third. Now there is an F block on the periodic table. It's these rare earth metals that are kind of pulled out to the bottom. Technically, the F's don't start till the 4th and 5th energy levels, but we're not going to have to worry about them. There's even some discrepancies in the scientific community on how these F orbitals would behave. So you're not going to be asked to write electron configurations for uranium or anything super crazy like that. Now, the last thing that we should mention is that sometimes these electron configurations aren't super wacky. You know, if I were doing somebody like fluorine, element number 9, I got to start at the beginning, 1s2, then I go to the 2s for 2. Now I'm at beryllium. I'm going to go across to the 2p, and fluorine is 1, 2, 3, 4, 5th element across. Done. If I were asked to identify the element, I can just look for the 5th element across the 2p block. Or you can add up all these little superscripts, and you get a total of 9 electrons. Element 9 is fluorine. When the elements start getting a little bigger, do you remember there's this noble gas shortcut? So the noble gases are this group, helium, neon, argon, krypton, xenon, radon. They represent atoms where all the orbitals are full. And what we can do for a little shortcut is to say, all right, let's say I want to do the configuration of calcium. So here's calcium, number 20. Do you remember the shortcut that you can go backwards to the previous noble gas? So the previous noble gas from element 20, calcium, would be argon 18. You can put that noble gas in brackets, and then you only have to write the orbitals that would come after argon. So you can really just then start in the row of your element. You can just say argon 4s2. Argon represents 18 electrons, and then 19 and 20 are in the 4s. What's kind of cool is that when you shorten up these electron configurations to the noble gas configuration, you're really just showing the outer electrons, the valence electrons, and in the end, those are kind of the most important ones anyway. The valence electrons are involved in bonding and chemical reactions. The inner electrons, or we call them core electrons, are all pretty stable. They're all in full orbitals, and they're usually not involved in bonding or reactions. So it's kind of a nice shortcut, and it really does show us the most important electrons. Now, if you were somebody like nickel element 28, I could do a shortcut too. So let's see, 30, 29, 28, maybe here would be nickel. So yeah, if you want to do this shortcut, you got to go backwards to the previous noble gas. You could say argon in brackets, and then I only have to write what comes after. So I can say 4s2, 3d. Nickel should be the 8th element across. So hopefully this brings back great memories from first year chem of using the periodic table to map out the electron structure of an atom. The periodic table helps us to predict the filling order, how many electrons go in each orbital, as long as you can mark up your periodic table.